done during my PhD in laboratory meteorology dynamic. So I derived a new product of surface LongWave cloud radiative effect using CALIPSO observations at global scale, and I will present at the end an application in the Arctic region. I worked with Ellen Schaffer during my PhD. I will start with a context, scientific context. In a stable climate, the incoming solar energy is almost counterbalanced by the outgoing energy. So the solar radiation would be balanced by the long wave emitted by the climate system and the short wave reflected. But today, because of human activity that is adding greenhouse gases into the atmosphere, we are keeping more energy in the climate system. So we have an excess of energy which is accumulated in the ocean mostly. 90% of this energy is in the ocean. Thanks to the satellites that are orbiting around the Earth, CRS for instance, we are now able to measure at the top of the atmosphere this excess of energy. So this figure, the last figure, shows the net COA radiation in red measured with CRS. So it's the incoming solar energy minus the outgoing energy. And we see that it is positive, so we are accumulating energy in the climate system, and it is increasing with time. So with this excess of energy in the climate system, the surface temperature is increasing, and with that we observe many climate change, such as more dryness, forest fire, the ice melt, and clouds are changing too. And me, I am interested in that virus called cloud. If we look at the component of the energy budget, at the top of the atmosphere, we have radiative fluxes only. So the short wave coming, the solar radiation in the short wave and the reflected in the short wave, and the outgoing wave radiation. At the surface, we have a radiative convective energy budget. So the radiative fluxes are not in balance. They are almost counterbalanced by the convective fluxes, which will create cloud in the atmosphere. And this cloud would affect both the top of the atmosphere and the surface energy budget. So at the surface, they will reflect part of the incoming solar energy and reflect it back to the top of the atmosphere. So they will cool the surface, and in the long wave, cloud will block part of the upward long wave radiation and reemit it down toward the surface. So they will warm the surface in the long wave. And me, in my PhD, I was interested in this last portion, so the long wave cloud radiative effect at the surface. It is not well known at the global scale because it depends largely on the vertical cloud distribution. So we need to observe that at global scale. And also it is important because in polar region, it may affect the Arctic ice melt. If we look at, so the surface long wave cloud radiative effect is quantified through the difference between all sky fluxes. So if we put a cloud into the climate system, minus the clear sky fluxes, the downwelling, upwelling, clear sky fluxes. So when the cloud radiative effect is higher than 0, this means that cloud warms the surface. So if we put a cloud into the climate system, it will increase the downwelling long wave radiation and therefore warm the surface. This cloud warming depends mostly on 3 cloud properties. The first one is the cover, which quantifies the horizontal extent of the cloud. More the cloud cover is high, the cloud will block more upwelling long wave radiation and therefore will warm more the surface. The second one is the optical depth. Opaque cloud will be at higher emissivities, so they will emit more long wave radiation toward the surface. And the last one is the altitude of the cloud. So cloud at low altitude would be at warmer temperature and therefore will emit more long wave radiation toward the surface. So we need to quantify this, to observe these 3 cloud properties to retrieve the cloud radiative effect at global scale. If we look at the state of knowledge of the cloud radiative effect in climate model, we have a large spread between the different version of CALIPSO model, for instance, and at the top of the atmosphere, the spread between the climate model is smaller than at the surface, because at the surface it's not we need more observation to constrain the climate model. And if we look at the state of knowledge of the cloud radiative effect using observation at the surface, so we have the ground station, for instance, the BSRN network that measures the cloud radiative effect, but they are mostly located over continents in the northern hemisphere. From satellite perspective, there are 3 products that exist. The first one is the CRS EBA that uses mainly radiometer, so CRS and MODIS. They derived their product between 2008 and 2023, so on 23 years, long time period. but they are limited in polar regions where the radiometer will be limited in detecting cloud over the bright surfaces. There are two other products that combine both active and passive remote sensing, so the CRS CCCM product and the 2BFLX product, HR, sorry. And they combine radiometers, CALIPSO Lidar and CloudSat radar. But since CloudSat has encountered a battery anomaly in 2011, their time series is limited to 5 years only. So if we look at CALIPSO alone, it has been observing cloud for over 16 years, and it is really about everywhere since it uses active remote sensing. So in my thesis, I will use only observation from CALIPSO to derive the cloud-Radiative effect at the surface. So this brings me to my outline, the outline of my presentation. I will start by presenting the method that I follow to retrieve the cloud-Radiative effect at the surface. And then I will evaluate it against the independent observation. And in the second part, I will look at the link between the cloud-Radiative effect and the Arctic sea ice falls. So for the retrieval of the cloud-Radiative effect, I use observation from CALIPSO only. I use the radiative transfer code to simulate the cloud-Radiative effect at the surface. And I will present the result, the linear parameterization that I developed and the retrieval of the cloud-Radiative effect. So CALIPSO have been sampling the atmosphere vertically over all types of surfaces. So here we can see the total attenuated backscatter signal at 532 nanometers. So we can see high cloud, mid cloud, etc., and low cloud. For each CALIPSO profile, we have here one profile of CALIPSO. We can see the attenuated backscatter in blue, and we can calculate the scattering ratio, which allows us to detect the cloud for each profile. So here, the scattering ratio, when it is higher than 5, we can detect the cloud, the top of the cloud, and the bottom of the cloud. If the signal penetrates through the cloud, we can observe an echo from the surface. So we classify this cloud as thin. If we are completely attenuated within the cloud, it will be classified as an opaque cloud. So for thin cloud, we are able to retrieve the optical depth of the cloud using the signal below and above the cloud, and from that retrieve the emissivity of the cloud. So each CALIPSO profile is classified as clear sky when no cloud is detected, as thin cloud when we penetrate through the cloud, so we can retrieve the mean altitude of the cloud and its emissivity. And for the last one is in opaque cloud, we will be completely attenuated at an altitude that we call Z fully attenuated. And so we can retrieve the mean altitude of the cloud, but not see the bottom part of the cloud. And the emissivities of opaque cloud is between 0.8 and so these 3 cloud properties that I will be used to retrieve the cloud-Radiative effect. Here I show the gridded maps of these 5 cloud properties. The first 2 lines are the cloud covers. So for opaque cloud on the left and the thin cloud on the right. So opaque clouds are the most dominant one at global scale, since they cover 42% of the globe. They are more numerous over Southern Ocean, over mid-latitude ocean, in the deep convective region, and in the stratocumulus region too. Thin clouds are more homogeneous around the globe, and they cover only 25%. They are a little bit more numerous over the Greenland and the Antarctic, where the dry atmosphere will favorize the formation of thin cloud instead of opaque cloud. The 2 other maps represent the altitude of cloud, the mean altitude of the cloud. For both opaque and thin cloud, they show almost similar behavior when we have high cloud in the deep convective region, so in the warm pool along the HCZ and also above continents, and cloud are at low altitude in the stratocumulus region, so here in the west coast of continent and over the Southern Ocean and mid-latitude ocean, where the cloud will be at 2 to 3 kilometers. The last map is the emissivity of cloud. So it is higher in the deep convective region also, and along the shallow clouds and over continent. To parameterize the cloud-Radiative effect as a function of these 5 cloud properties, I use a radiative transfer code. Here I present how I do one radiative transfer computation. I do the radiative transfer computation for each month and each 2-degree latitude band. So here for simulating the clear sky fluxes, I take atmospheric profile from reanalysis, so humidity, temperature, pressure, and ozone. With the radiative transfer code game, I can simulate the downwelling and upwelling clear sky fluxes. To simulate the all sky fluxes, I just add a cloud into that framework, keeping the same atmospheric state, so the same humidity and temperature, and pressure, and ozone profile, which allows me to have the all sky downwelling and upwelling fluxes. So with that, I can calculate the cloud-Radiative effect, which is the difference between the two, the all sky net fluxes and the clear sky net fluxes. So from that, I parameterize the cloud-Radiative effect as the function of the emissivity and the altitude. And here I show the results, which represent several radiative transfer computations. One example for one atmospheric state. Each dot here represents one radiative transfer computation. The shape represents the geometrical extent of the cloud. So 1 kilometer is a star. And when the cloud is extended in 6 kilometers, it will be the cross. And the color bar represents the top altitude of the cloud. So the dark one are cloud that has top altitude that is close to the surface, and the lighter one is higher top clouds. What we can see on this figure is that all the simulation lines up, and the cloud radiative effect depends linearly on the mean altitude of the cloud. So it doesn't depend only on the bottom part of the cloud, but all the layers of the cloud will emit radiation toward the surface. So from this simulation, I can derive this linear parameterization, the cloud radiative effect as a function of Z opaque with the coefficient A and B. For the thin cloud, I just vary the emissivity of the cloud, and the cloud radiative effect will increase when we increase the emissivity of the cloud. So for the thin cloud, it will also depend linearly on the thin emissivity of the cloud. So this example of simulation are over ocean for January at a latitude of 39 degrees. But since humidity and temperature largely vary across the different months and different latitudes, I did also several radiative transfer computation for above ocean and above land for each month and each 2-degree latitude band. And here I show the behavior of the coefficient A and B. You can retrieve the one that I showed previously here for A and B. And the shape of these curves are really driven by the shape of the humidity and temperature in the atmosphere. So the coefficient A and B depend also on the humidity and temperature. Another thing that we took into account is the surface elevation over continents. So over continents, the high surface elevation will be drier. So the cloud radiative effect will be more important. For instance, here a cloud will warm more surface with 4 kilometers, for instance, this cloud. Oh, sorry. Then the surface that is close to the ocean. So the coefficient A and B will depend also on the surface elevation above continents. So to derive the retrieval of the cloud radiative effect using CALIPSO, I just take observation from CALIPSO and put them in this linear parameterization. So here along along CALIPSO orbit, for instance, here a cloud, the blue one, which is a cloud at 30 kilometers, will warm the surface by almost 20 watts per meter square, using the parameterization that before. And also, we can derive the gridded cloud radiative effect using the gridded cloud properties. So here, the cloud radiative effect at global scale is equal to 27 watts per meter square. Clouds warm more the surface over the ocean, in the southern ocean, where they are really opaque and close to the surface, so warmer, and emit more radiation toward the surface. And in the tropics, they warm more in the stratocumulus region, which they are really opaque and close to the surface.
So,
Yes.
do you compare to what other people like series?
Yes.
Sorry, I'm a plant though. Go ahead.
So this is the retrieval of the cloud radiative effect, and now I will compare it to the other product. So I compare it to long orbit scale, orbit track. I collocate the different products at the orbit scale, and also I compared the gridded product into the ground station. So here, I took 4 pieces of orbit in different atmospheres. In the East Pacific Ocean, the shallow clouds, autonomous region, and Antarctica. The product that I derived is in red, so LongWave CRE Lidar. The CRS CCCM product is in green, and the 2B FLX HR is in blue. So here, CRS CCCM and 2B FLX combine both active and passive remote sensing. We can see that the 3 products show similar behavior and agree pretty well along the orbit. And also we have good correlation between the different products for both high, mid, and low cloud for different type of clouds. But locally, we can observe large differences. For instance, here in the deep convection region, where the ladder will be completely attenuated in the higher layers of the atmosphere, and we will not see the bottom part of the cloud. For instance, this high cloud, there is a low cloud lying beneath this high opaque cloud, and we cannot see it. So locally, we underestimate the cloud radiative effect by values that can go up to 50 watt per meter square. Now to see how much these differences occur, I collocated the different products along orbit scale. So here, for instance, I show how I collocated my product with the CRS CCCM product, which has a 20 kilometer resolution at the surface. So the red spot. CALIPSO profile are just these small black dots within the CRS footprint. So in each footprint, I calculate the cloud radiative effect for all profile and then average them and compare the two. And the results are shown on this figure. So we can see that both of them aligns well and like around the 1 by 1 line. Although we can see one pattern that goes away from the 1 by 1 line. And this pattern also we can observe it with the collocation between the 2B FLX product. And it's occur in deep convective region. So it's for high clouds, and the LiDAR will be completely attenuated and we will not see the bottom part of the cloud. So here we underestimate the cloud radiative effect by almost 50 watt per meter square, and they occur 7% of the time in the deep convection region. Another pattern that goes away from the 1 by 1 line is this one for high values of cloud radiative effect. And here it's the LongWave CRE Lidar that overestimate the cloud radiative effect compared to the other 2 products. This is located over low marine mid-latitude cloud, and it's mainly due to the humidity and temperature profile that I am using, which are different from the other one, from the CRS-CCCM product and the 2B FLX product. Although the comparison with the 2B FLX product, HR, I see this pattern where the 2B FLX product overestimate the cloud radiative effect compared to the CRS, the LongWave CRE Lidar, and it's occur everywhere around the globe. So I couldn't really know what was the cause. One would be that sometimes the radar has an echo from the surface and over-detect cloud in the boundary layer, and CALIPSO doesn't. But I haven't investigated further, because I don't see it in the comparison with the CRS system. And now here I compare the gridded products. So in the first one as zonal means, always the Lidar product in red, the FLX in blue, and CRS EBAF in green. Here I use the CRS EBAF, which is gridded, because the CRS CCCM is not gridded. And the CRS EBAF is only derived through passive remote sensing. So we can see that in the tropics and in the mid-latitude, the 3 products agree together, and we find similar patterns. But when we go to the polar region, the CRS EBAF gets to be higher than the other 2, where we overestimate the cloud radiative effect compared to the other 2 products. If we look at the map of differences, the LongWave CRE Lidar and the 2B FLX Lidar agree pretty well together, especially in polar regions where we have small differences. The maximum differences occur over continents where we have high surface elevation, higher than 3 kilometers. When I compare the 2 products derived from active remote sensing and the CRS EBAF, I found the similar differences in the polar region. So here over Antarctica and over Greenland, where CRS EBAF tends to overestimate the cloud radiative effect compared to the other 2. So here it's due to MODIS, the radiometer that over-detects cloud over polar regions, over polar bright surfaces. Now I compare the three satellites product to the ground station, which are the reference for retrieving the cloud-Radiative effect. In three locations, the first one is in polar region over the Arctic, over Greenland, sorry. So here, between 2008 and 2011, I can see that the cloud-Radiative effect from Lidar is agree better with the 2BF helix product than the CRE, where we find similar seasonal cycle and maxima and minima at the same month. And the CRE product is shifted in time and find maxima where we have the minima, so for instance in winter. And when I compare to the ground station, which is only available between 2011 and 2016, here the LongWave CRE Lidar agree very well with the ground station. We find the similar seasonal cycle with the maxima at the same month, but we underestimate the cloud-Radiative effect during winters because of CALIPSO not seeing some thin clouds that are near the surface, which was shown by the 2017. But here also CRE find a shifted, a seasonal cycle that is shifted with maxima during winters compared to the ground station. Here I compare the three products in a station that is in France, in the mid-latitude France. Here, the three products agree well with the ground station. We find good correlation between the different products, and the bias is smaller than polar region for all of them. And the same for the tropics one, where the seasonal cycle is flat, but the bias is smaller. So when we look at global scale, between 2008 and 2011, the CALIPSO product, the LongWave CRE Lidar in red, agree well with the 2BF helix product, the blue one, but the CALIPSO one stays for more than 10 years, so until 2021. The CRE product that is available for more than 10 years is shifted in time compared to the other two products because of the over-detection of cloud in polar regions during the winter. So for the conclusion of my first study is that CALIPSO allowed us to retrieve the cloud-Radiative effect between 2008 and 2020. The maximum local differences occur in the gridded product over surfaces with high elevation, and we can reach 30 watts per meter square. And for the instantaneous product, we have maximum local differences in the deep convective region that can reach 10 to 50 watts per meter square, but they occur only 7% of the time. And the most important conclusion is that CALIPSO allowed us to have 13 years of surface LongWave cloud-Radiative effect, which is reliable over polar regions. And this result was published in Atmospheric Measurement Technique journal. Now I will use this product that I derived to look at the link between the cloud-Radiative effect, the cloud warming, and the Arctic sea ice loss. So I'll present a context, the method that I followed to isolate a region where the Arctic and the Arctic sea ice varies, and present the result, the distribution of the cloud warming within that region, and split them into over open water and over CS to see how they affect the sea ice formation. This figure presents the surface temperature at global scale. Here we have the latitude, so at zone and mean, and the evolution over time. The blue spots represent negative anomalies, and the red one represents positive anomalies. We can see that the surface temperature is increasing everywhere over time, but we can see that it is increasing faster in the Arctic region, so called the Arctic amplification. The Arctic has warmed nearly 4 times faster than the rest of the globe. Because of global warming, the Arctic is losing sea ice, so it is accumulating more shortwave into the ocean, which creates greater warming and more sea ice loss, which creates a positive feedback. But if we add the cloud into that framework, during summer, the cloud will reflect part of the shortwave radiation, so they will cool the surface, and therefore they will create a negative feedback. But if we add a cloud during winter, during non-summer season, this cloud will just absorb the upward and downward radiation and remit it down toward the surface. So they will warm the surface and amplify the Arctic sea ice loss. Observations showed that there is a coupling between the atmosphere and the ocean during non-summer season that will favorize this formation of low-level cloud. So they will increase the downward LongWave radiation and amplify the Arctic sea ice loss. But they didn't quantify by how much they will warm the surface. So here we look at how this low-level cloud can change surface warming during fall. If we look at the seasonal cycle of the cloud radiative effect, the red one is the long wave, so the warming effect. The blue one is the short wave, so the cooling effect. During summer season, where I have both the short wave and the long wave components, the short wave cooling effect of clouds is larger than the warming, so clouds cool the surface. But during all other seasons, non-summer seasons, they warm the surface, and especially in October, which is the maximum of cloud warming. On average, over all the Arctic, they just warm the surface by 61 square. October is an important month to look at the covariability between the cloud warming and the sea ice loss, because during October, from months where the sun is setting and we have just the warming effect of cloud at the surface, October has lost a lot of Arctic sea ice. If we compare the pink curve to the blue one, October has lost 2.8 million of kilometers square of sea ice. And also October is the month where the Arctic sea ice starts to refreeze, so to reform. And also the cloud warm the surface the max during this month. So here the question is, do this October cloud delay the sea ice freeze up later into the fall? To answer to this question, I relied on previous work of Morrison et al. That isolate a region in the Arctic where the daily sea ice cover varies. So I split the Arctic into two regions, delimited by two masks, the perennial mask and the intermittent mask. So the perennial mask, the gray one, isolates a region where the daily sea ice does not change. So it contains continents, grid boxes that remain always ice-free, and grid boxes that are always ice-covered. The pink one, the intermittent mask, isolates region where the daily sea ice varies. So one day it can be fully overcast by sea ice, and the other one fully open water. And we assume that in that region, the local processes would affect more low cloud than large-scale atmospheric circulation. And here I use one by one gridded for that. So I gather all the CALIPSO profile falling within that region and look at the climatology of cloud. And we can see that through the entire intermittent mask, it is really cloudy, since clear sky occur only 30% of the time. And most of these clouds are opaque. Opaque cloud covers 52% of the intermittent mask, and they are more located on the edge of that region. And the thin cloud covers only 29% of the intermittent mask, and they are more located here, which is the coldest region of the Arctic, which tends to form the thin cloud instead of the opaque cloud. When we split this cloud into high and low, delimited by 2 kilometers, most of these opaque clouds are low. They are at altitude lower than 2 kilometers. They occur 27% of the time. And these low opaque clouds are the ones that warm more the surface. So next, I will just focus on this low-level opaque cloud. I split them into over open water and over sea ice. So for each CALIPSO profile, I look at the concentration of the sea ice. If it is lower than 20, it is over open water. If it is higher than 80%, I classify it as over sea ice. So here we can see that the low-level opaque clouds occur everywhere, and they occur more often over open water than over sea ice. That over open water, they are 33% present, and over sea ice, only 21%. And this low-level opaque cloud, they will warm the surface more than the other cloud, which result in these two maps. So the cloud radiative effect over open water is way larger than over sea ice. It's 47 watts per meter square when average over the entire intermittent mask. So this difference in the cloud radiative effect being higher over open wire than over CIs is mostly due to the low cloud. Here I show the distribution of all profiles of all values of cloud radiative effect in the instantaneous product located over the intermittent mass. The blue one is over open wire and the light blue is over CIs. So for thin clouds, high clouds, and low cloud. We can see that this low level cloud warm the surface by values higher than 80 watt per meter square, and also that occur much more frequently over open wire than over CIs. So as the climate warms and we'll have less CIs in the Arctic, we'll have more open wire, which will have more low level cloud that will warm the surface by 80 watt per meter square. To see how it might evolve in the future as the climate warms, I compare October to November because November has much more CIs, and in the future, as the climate warms, November may look like current October, and future December may look like current November. And November shows that we have also large values of cloud warming caused by low-level cloud, so higher than 80 watt per meter square, and they occur much more frequently over open wire than they do over CIs. So this cloud warming will persist later into the fall and may delay the CIs result. So as conclusion for my second study is that high values of surface cloud warming, higher than 80 watt per meter square, occur much more frequently over open wire than over CIs. And as the climate warms, these low-level clouds that form the surface by values higher than 80 watt per meter square may delay the CIs result later into the fall. So this study is accepted in GRI, but not published soon. Yes.
So maybe this is the next thing you're going to show. I don't know. So instead of doing October versus November as a surrogate for climate change, you've got a really long record. Have you looked at the change in low cloudiness over the CALIPSO record?
Like look at the months where I have just isolate the months where the CIs is really low and isolate the month where the CIs cover is high and just compare the two.
Well, I mean, we know that the sea ice is reducing. So according to your hypothesis, and this just shows my ignorance of the cloud feedback literature. Do we see low cloud cover increasing over those places? Like if you look at the Arctic, so the sea ice is decreasing. Well, according to what you're implying, that low level cloudiness should have increased. Did it?
Actually, I haven't looked just at the time series of the cloud cover in the Arctic to see how it will if it increases when the sea ice is decreasing. But yeah, I haven't looked. But yeah, since we have less cover of sea ice, it will create more low-level clouds. So the cover of low-level cloud should increase.
I mean, maybe someone's already did it, but it seems like an obvious thing to check.
Yeah.
Is there enough data per year to do such an analysis?
Yes, since I'm using the instantaneous profile, so we have a lot of profiles running within the polar region, and over the polar region we have more overpass of the CALIPSO satellite. So yeah, we can look for each year separately and see how it evolved through the 13 years time series. Yeah. Yeah, it was not the next thing that I will show. I was going to arrive to my conclusion, to my general conclusion, which is that CALIPSO observation allowed us to retrieve the cloud radiative effect over 13 years. And this retrieval can be lengthened further in the future with the future satellites, such as the EarthCare and iOS, if we are able to reconcile the different missions, since they are not using the same wavelength, they don't have the same time of overpass. So we will see. And also that cloud warmed the surface by values higher than 80 watt per meter square in response to Arctic sea ice loss, and they might amplify delay the sea ice freeze up later into the fall. So for my perspective, one thing is to look at the surface cloud radiative effect in the climate model, in CALIPSO model. If we look at the top of the atmosphere, we have a smaller spread between the different models in simulating the top of the atmosphere cloud radiative effect compared to the one in the surface. So at the surface, the different climate models really disagree on simulating the cloud radiative effect. We have large spread in the deep convective region and over the Southern Ocean region. And we don't observe this spread in the observation, where they agree with each other, except in over polar regions, over the Arctic and Antarctic. So one way to look at why they have this disagreement between the different models is with my method, with my parameterization, and I can calculate the cloud radiative effect in the climate model when they have the COSP simulator implemented and the opaque cloud, the opaque diagnostic, so they can retrieve these 5 cloud properties that I'm using and to see why it's not well represented at the surface.
Which observations is the inter-observation spread coming from?
Which observation? So the 3 products, CALIPSO, the one that I developed, CRS, EVAF, and 2B affiliates. Same at the top of the atmosphere and the surface. And for the climate model, here I show CISS, MERA, CESM2. I don't remember which other, sorry. Yeah. And for my current work here at GISS, I work on low-level cloud feedback. So I separate stratocumulus from cumulus. Greg developed a new dataset called Cascade, where he separates stratocumulus from cumulus. He also developed a method where we can separate stratocumulus from cumulus in the climate model and also in observation. I extend this method into the entire globe instead of only the tropics. And we can see that here I use the method using CALIPSO observation, the GOCCP product, and we can retrieve similar pattern as in the observation, the Cascade product, with big pattern of stratocumulus in the west coast of continents and also in the Southern Ocean. And we have also like good global average between the two data sets. I can apply this method to the climate model. So here model E3, sorry. Here E2.1, sorry, and the CALIPSO model. So in model E3, we have also good pattern of stratocumulus in the west coast of continents in the tropics. But over the Southern Ocean, we have less stratocumulus than the observation. But when we look at the model E2.1, we have a better representation in E3, since in the E2.1, we don't have this pattern of stratocumulus in the west coast of continents. And yeah, so there is a better representation of low cloud in model E3. And when I look at their cloud feedback, so here in the pink one is the Cascade cloud feedback. The red one is the stratocumulus cloud feedback, and the blue one, the cumulus feedback. You can see that CMIPSIS model has find cloud feedback that are close to the observation, or the cumulus and the stratocumulus one. The model E2.1 has negative feedback, which was biased. And in the last version of model E, so E3, we have better representation of stratocumulus and cumulus feedback, especially for cumulus, which are close to the observation. And for the stratocumulus one, some of them have better representation than the others. For instance, the 698 and the 705. The worst one are the default and physics. So the next time in the future, I will look at the tuning parameter of the different versions and see why some of them perform better than the others, etc. But it's really like not far, how do we say, like new results that I read, not far, not a long time ago. So yeah, that's it for me, and thank you for listening to me. Yes.
What's the like physical mechanism between low-level clouds and less sea ice in the Arctic? Like, is there like do you know what that is?
Why do we have more low-level cloud when we have less sea ice?
Yeah.
Just because when you have less sea ice, you will have more open water, which will favorite the formation, the transport of humidity in the lower troposphere, which will form this low-level cloud.
Okay.
When you have the sea ice,
So it's just the more water. Okay.
yeah, but also like the profile of temperature and humidity will be more. They call it coupling between the atmosphere and the ocean,
Cool.
which will tend to create this low-level cloud over open space or over sea ice.
Nice.
And like when I showed the distribution of the cloud radiative effect, and for instance, here I found more over open wire than over sea ice, but over sea ice also I have this small increase. And we think it is due to low-level clouds that are formed over open water and that are transported into over sea ice. But I haven't looked at that. Another PhD student of my supervisor is looking at that using wind and to see if it's the low clouds that are uplifted over sea ice or that are uplifted from open water to over sea ice.
Using Aeolus or like the new wind or no?
He tried to use what's the name of the satellite that is observing wind.
Is it Aeolus or is that?
No,
that's the
Sea whips,
instrument.
maybe?
No, it's Aeolus.
That's
Yeah.
that's what I'm
Aeolus.
saying.
Okay.
Yeah.
Aeolus. It's the Aladdin lidar. But I think in the polar region he couldn't really find the good representation of wind,
Mhm.
so he's using reanalysis.
Okay.
So Jean.
I have a question. So on your slide 39, I was just curious were those a long wave and short wave from the 2B Fluxar LiDAR that you were using
Yeah.
for those? Okay.
Actually, here in for the full line, for the straight line is the 2BFX product that I'm using.
Uh-huh.
Because in the LongWave CRE, we
Mhm.
just have LongWave, we don't have the shortwave. So that's why I'm using the 2BFX product.
Uh-huh.
And the dashed line is from the LongWave CRE LiDAR.
Okay,
So
cool.
that's why for the red one I have two, and the other one is just one.
And that's kind of my follow-up question is there plans for creating a shortwave CRE product, or is it rather challenging?
I think it is challenging because
Yeah.
in the long wave it depends on the opacity, altitude, and the cover. In the short wave, it will depend highly on the microphysics of the cloud.
Mhm.
And with the lidar, we get I don't know, like we get attenuated in opacities between 3 and 5, and the shortwave cloud radiative effect is sensible until opacities that can go up to
Yes.
50 or 30.
Yeah, that's like an exponential
Yeah,
increase.
exactly.
Yeah.
So I don't know if we can see that with the CALIPSO. We tried to do that a bit, but we didn't explore it further because it was complicated a bit.
Yeah,
Just doing it with CALIPSO and not.
I imagine.
Yeah.
Yeah, cool, thanks.
I have a question that you were talking about for your conclusion slide. You were saying that your retrieval can be applied to future planned instruments.
Yeah.
The biases that you were seeing with your retrieval compared to the other observation sets. This is just I'm naive about
Mhm.
these different instruments, but do you think some of those will be addressed, or you think those biases, for example, with the deep convective class, you think those will still be there?
Okay. Here I said that it can be lengthened with future spaceborne lidar. So the spaceborne lidar will be also attenuated in the deep convective region, so we will not see the bottom part of the cloud. A way to improve that is to combine both lidar and radar, because the radar penetrates through the cloud and we can see the bottom part of the cloud. But I didn't use it because we have only 5 years of CloudSat.
Okay.
But yeah, EarthCare has lidar, radar, and radiometer, so yeah, we can have all the synergy of the different instruments, and that will not be the length and just of this product, because mine is biased because of this bottom part of the cloud that I don't see.
We do have a comment in the chat from Gavin. He said there was a paper a while back that looked at the cloud CS interaction on albedo.
Mhm.
So if you want to take a look at that, he put the link.
Okay,
In
thank
the-
you, Kevin.
And do we have any other questions?
Is there a connection between like the Cloud-Aerosol effect and the thickness of the cloud, or is it just the mean amplitude?
Here I separate opaque cloud from cool cloud. So for opaque cloud, their emissivity is between 0.8 and 1. So they like the cloud radiative effect at the surface for all opaque cloud is close to each other. But for thin cloud, yeah, it increases with the opacity and which is also increasing with the emissivity.
As Andy was suggesting, I mean, it should be easy for you to do a feedback parameter like T-cloud cover DCIs,
Yeah,
using different timescales of change of CIs.
Yeah.
annual mean, seasonal cycle, whatever. You can use anything for TCIs. And then look at the cloud cover. I mean, you have the best potentially available observations and derive a feedback parameter of that sort. I mean, I've seen people look at changes in CIs and changes in cloud, but nobody's deriving like a quantitative measure of the relationship.
We started doing that. We were not calling it cloud feedback, because cloud feedback, usually people look at the top of the atmosphere.
It's not a feedback, because there's
Yeah.
a lot of other things that go in. It's not a
Yeah.
closed loop. I mean, wind plays a role. I mean, a lot of the cloud can be transported into whatever area you're using in CI. So it's not going to be a feedback, but it's going to be a parameter that's useful to look at.
Yeah, how the cloud-Radiative effect varies when the CIs varies. So look at the covariability between the different parameters or compared to the variability of the CIs.
Yeah, because the story is really obvious that more open water, you have more evaporation, you should have more clouds. But do you, first of all, because other things also play a role, and the second is how much? I mean, quantitatively, what's that relationship looking like?
Yeah, it's interesting. I will try to look at that.
Okay, yeah, if we don't have any other questions, we can just give another. Thank you.
Thank you.
And you're around GISS, right? So
Yeah.
if people want to stop in and chat, can I offer?
Yeah, of
Okay.
course.
Now we know what Assia does, so we can stop in and chat.
She has a sign on the door. You have a sign on your door?
Yes.
Yeah, you did, okay.
Thank you.